Okay, you guys, today we talk about sample proportions. Specifically, we will look at how likely we are to achieve a certain sample from a population. Now, this will be really interesting because up until now, we've only been able to calculate probabilities for certain individuals or certain one-shot events. But now we will be able to use the principles of what we learned about sampling distributions and apply to that general rules of probability. And what's even better is we are going to find that we get to use the same ideas that we've already learned with z-scores. So much of this is going to look pretty familiar to you. Now, let's go ahead and make sure you have your EQ and your assignment written down, and let's get to it. Alright, so what is it we need to know in order to calculate the probability of a sample having certain characteristics? Well, we need to know the properties of the distribution of all possible samples, and what this means is we need to look at sampling distributions. Okay, so what that means is we're going to look at a bunch of different samples where I'm looking at proportions from the same population. Okay, so let's give an example that you guys just took a test and I wanted to get a feel for how well students felt they did. What percentage of students felt they were successful? So let's say, I don't want to get a survey from everybody, but let's say I take a small sample of students and about 70% of them said they were successful. So that's a p hat. Now I go and I sample another set of students, and these guys were, much more of them were confident, and we had about 80% say they were successful. But then I had another sample that I took, and only about 50% of them said they felt they were successful. And so let's say I take several of these samples. Okay, what ends up coming up here is something that is not unlike a sampling distribution. Remember, a sampling distribution is just going to be something where I have multiple samples, all of the same size, recording the same characteristic or same statistic. And in this case, all of these p-hats are representing the proportion of students that felt they performed pretty well or successfully on this last test. Okay, so every one of these is just proportion, and then once we start to see that we take a whole lot of these proportions, a lot of these samples, we find that it's going to fit some kind of generalized shape. Now, sometimes that shape looks really familiar to us and can actually be really useful. So we want to know the shape, because if we know the shape, then we have a general idea of how the whole thing is going to be behaving. Specifically, we hope it's going to be normal. If it is normal, then we know we can apply lots of different probability rules. Okay? The other things that we want to know about is, well, what's the typical proportion that I'm going to see? On average, what percentage of students would say they were successful? In that case, we end up looking at the center of that distribution, and we would call that the mean. What's the average percentage of students that would say they were successful on this test? But then I also need to know what the spread is like. Okay? I know that not everybody is going to say the same thing, so I need to know how much everybody varies from each other. So when we look at spread, that means we're going to generally be looking at standard deviation. So what's the sigma sub p hat for this, all possible samples? Okay. So the big challenge for me is calculating this mu sub p hat. How am I supposed to calculate the average proportion of students that would say they were successful on this test? How could I do that without taking a whole bunch of samples? Well, actually, this is going to flow really nicely and be able to be derived from everything we did in the last section, in the last chapter. So I want you to imagine a binomial variable called x, where x is the number of successes in some chance event. And this is something that we can consider being binomial because, hey, a student says they were successful on a test or not. Each student is independent of the next one. We can look at it in that lens then. So remember, we calculated formulas for the average number of successes in some kind of chance event like this. That was mu sub x. And mu sub x was equal to n times p. We did this in the last chapter, and then we also found the standard deviation, and that was square root of n times p times 1 minus p. Okay, and so what I'm actually going to want to do is, I don't want to think about this in terms of number of successes anymore. I want to think about this as, well, what's my probability of success? Okay, so what we have to compare everything to is this value p, that probability of success. But we don't know what the probability of success is. We don't know how likely a student is to say that they were successful on a test. We don't know what's the total proportion of all students that would say they were successful on this test. So this is really just going to be some kind of claim. We don't know if it's true, but we're going to assume it's true, and then we're going to try and refute it. Now, the evidence we can generate to figure this out is going to be from at least one sample. So if we can take one sample, p hat, we can compare it to something that we believe to be true. Okay, so this p hat, this sample of students that would say they were successful, we can calculate this by taking the total number of students that would consider themselves successful and dividing it by the number of students we asked. So x divided by n, right? That is our sample proportion of successful students. And what this means is we can actually consider this transforming the random variable x, the number of successes, into the probability of successes in a sample, or p hat. Well, how do we do this? How does x turn into p hat? It does this by multiplying x by 1 over n. Since we are transforming the binomial random variable x by some kind of multiplication, that means we can change both the mean and the standard deviation into a mu sub p hat and a sigma sub p hat. We can now work with a different context. So let's see what that context is going to look like. Okay, so remember that multiplying changes mean and standard deviation. It's real simple. All we have to do is multiply mu sub x times 1 over n. And that will give us our new transformation. So if I were to multiply the mean of the random variable by 1 over n, that's 1 over n times p. Just using this formula that we had up here, and I'm transforming it by multiplication of 1 over n. And you notice what's going to happen with these n's here. They're going to cancel each other out. And what am I left with? I'm left with just p. So this actually is a huge statement for us. Mu sub p hat is going to be equal p. And what that tells me is the average probability of success in a sample is equal to the probability of success in my entire population. So what that tells me is, hey, the average proportion of students that would say they did well on a test is equal to the total proportion of students in my entire population that say they do well. So this is a huge, huge statement, and actually really easy for us then, because all we have to do is say we can compare what the average sample should look like for that claim that we're going to be looking at. Now, how about standard deviation? How can we change that? Well, we've got our sigma sub x, and we are going to change that again also by the same thing, multiplying by 1 over n. So we take our 1 over n and then we multiply it by that formula, square root of n times p times 1 minus p. And with some clever manipulation, I can see that 1 over n, this is exactly the same thing as if I take the square root of 1 over n squared. Well, why do I want to do that? Because look at this square root here. What happens if I plop that 1 over n squared inside the square root? Let's go ahead and rewrite this by putting it inside here. So that means I have 1 over n squared times n times p times 1 minus p. Now we can start to see, hey, it's the same kind of thing that we saw before. I've got an n here, and I've got 2 n's down here in a denominator, and that's now going to leave me with the following. Square root of p times 1 minus p all over n. And that is my standard deviation of p hat. So now we 3, 2, 1. So now this is actually really powerful for us because we now know what the center of the sampling distribution of sample proportions would look like, and we also know what the spread would be. If we know what the center and spread of all possible samples should look like, we'll be able to compare different samples and how likely they are to occur compared to one another. So let's take a moment and summarize how we can use this. Any random sample will be a member of the sampling distribution of p hat. And after examining characteristics of sampling distributions that you guys did in the last section, we now know how random samples tend to behave. And we can now identify the center, spread, and shape of a sampling distribution of p hat. So let's go ahead and take an SRS of size n from population of size capital N with a proportion of success p. Well, then the center of that sampling distribution is just very simply going to be the mean of the sampling distribution. And we just calculated, we just derived what the mean of p hat is going to be, and that's p. So mu sub p hat is equal to p. How about the spread? Well, the spread of the sampling distribution is going to be that same formula that we had, but we have to pay attention to a certain thing. Whenever we start looking at sampling lots of individuals, we have to meet certain conditions or criteria, and these are what we call our conditions for inference. Okay, one of these is called a 10% condition, and what that tells us is that our sample, lowercase n, must be less than or equal to 10% of the population size. It's a funny thing that happens if we would think, you know what, we want to have a large sample from our population. The larger the better, the more representative it's going to be. But funny things happen when we take too large of a sample from a population. We want our population to be sufficiently large. If we take too large of a population, then sometimes we get too many of the outliers, and that can affect the standard deviation a little bit too much. So long as the 10% condition is satisfied, we can use that formula that we just derived. The standard deviation of the sampling distribution of p hat is equal to p times 1 minus p divided by n, taking the square root of the whole thing. But again, this 10% condition must be satisfied, so we need to always look at what's our sample size that we're supposed to be taking and how big is the population supposed to be. If the 10% condition is not satisfied, then we simply cannot use this formula to calculate, and we have to make some other kind of assumption. So what are we supposed to do if we can't use this formula? Well, we kind of take the easy way out. In the context of this class, we would say, well, I'm going to go ahead and use this formula anyway, but I'm going to proceed with caution. But it's really important to state that, hey, you know what? I know this conclusion is not going to be very accurate. Otherwise, we could use a previous standard deviation from a previous study, something to that effect that's going to be related to this. That will help us make an estimate to how all of the different samples should be relating to each other. Okay? So now we know the center and we know the spread of what the sampling distribution should look like. Now we need to figure out the shape. Okay, and this is one of our other conditions of inference, but this is a really big one and really powerful for us. So as long as the number of successes and failures will be at least 10, then we're going to be allowed to assume that the sampling distribution of p hat is approximately normal. And that is a huge, huge thing. Okay, so why successes and failures must be at least equal to 10? Well, even though we want to have a small sample size relative to our population, we still need to have a large enough sample size to where we can make some kind of reasonable conclusions about things. So our successes and failures must be greater than or equal to 10. The other way we can look at this, instead of in terms of successes and failures, we can look at it as n times p, which really this is our number of successes, and then n times 1 minus p would really be our number of failures. Okay, we look at it using these two quick formulas, and if these two things are true, then we can say, you know what, this is going to follow an approximately normal distribution. And if this all follows an approximately normal distribution, we know the center of this is mu p hat. We know the spread of this is going to be sigma p hat. And when we know the mean and standard deviation of a normal curve, then that means we can do all kinds of probability problems. It means we can figure out what is the probability of a sample falling in this distribution. And hopefully you start to put it together. This is just like z-scores, which is exactly what we're going to do. So remember that z-score formula was z equals x minus mu over sigma, where x is our observed value. Well, what are we observing here? What data are we actually collecting? We're collecting a sample proportion, p hat. The mean is the mean of that sampling distribution, the mean of all possible samples. So that's mu sub p hat. And then our standard deviation is the sigma sub p hat. And this is our big money maker right here. This is what's going to be able to help us now calculate proportions or sample proportions, right? How likely we are to see a certain sample relative to all other possible samples, okay? All right, so now you can take a look at the examples. I recommend you look at them in order, but go ahead and click the buttons, example 1, 2, 3, or 4 to proceed. All right, so in the game of Scrabble, we have a player beginning by drawing 7 tiles from a bag that contains 100 total tiles. We have our total number of vowels, consonants, and blank tiles in the bag, and we have this player, Kate. She chooses an SRS of 7 tiles. We will let p hat be the proportion of vowels in her sample. So anytime I'm working with problems like this, again, I see lots of numbers here, I see lots of symbols, things are going off in my head. I'm going to write down some things off to the side. These are my givens, the things that I know. This is just good problem solving. It's like marking the text. My population size, my total number of tiles is 100. And from those 100, what's my sample size? 7, right? So from there, we can see, well, what proportion are we interested in? Do we have a p or a p hat? Well, we say let p hat be the proportion of vowels in her sample. So what's the total proportion of vowels in the whole bag? Well, that's 42 out of 100, or 0.42, okay? Which means my probability of failure, not getting a vowel, would be 0.58. So, part A for this, can you calculate the standard deviation of the sampling distribution of p hat? So, sigma p hat, we know that formula, right? It's this one, is square root of p times 1 minus p divided by n. But the problem is there was a condition that we had to check with this. Which condition was it that we had to check in order to be able to use this formula? It's the 10% condition. So, we want to know our sample size. Was it less than or equal to 10% of the entire population? Well, 7 is indeed less than 10% of 100. So that checks out, okay? You don't need to even write everything out, and especially once we identify and define all of our variables here, this is usually sufficient enough, and we would say, yep, check. Okay, that's done. But you can't just say 10% check. You have to actually write out the rule to show that you are going through the motions and you are checking this thing. So let's go ahead and calculate this thing now, because we are allowed to do it. The 10% condition is satisfied. So my probability of success is 42. My probability of failure, 1 minus p, is 0.58. And dividing that by my sample size. Every time I take a sample, I'm taking 7 tiles. And then I'm going to take the square root of that. When I go through the motions there, put that in the calculator, I'm going to get 0.1865. Double check my work in the calculator and make sure we have it, but there is our standard deviation of p hat. Okay, let's go ahead and take a look at the next one. Is the sampling distribution of p hat approximately normal? Well, which one of these conditions talked about our shape? That was the large counts condition, which you'll see me abbreviate as the LCC, and we want to know, was this satisfied? So in this case, we have n times p. Was it greater than or equal to 10? That's our number of successes. So n times p, in this case, we have 7 times our probability of success, 0.42. And is that greater than or equal to 10? No, it's actually not. 7 times 42% is less than 10. So in that case, I don't even need to check this next part, my number of failures, because it doesn't really matter. This was not satisfied. So no, the sampling distribution is not normal because the LCC is not satisfied. So the next question, if you drew 7 tiles and did not look at them, what would be your best guess for the number of vowels you would have? Well, we want to think about, well, what was our mu of p hat, right? That's the typical sample proportion of vowels. Mu sub p hat is supposed to be equal to p. which is 0.42. But the question is not really asking about it in terms of the proportion, right? We're going to have to multiply this by our total number in our sample. So 0.42 times 7 is going to be, it's 2.94, which let's go ahead and, since we're looking at number of tiles, we can go ahead and say that's going to be approximately 3 vowel tiles. That's example number 1. Let's go ahead and take a look at example number 2. All right, so Harley-Davidson motorcycles make up 14% of all the motorcycles registered in the United States. You plan to interview an SRS of 500 motorcycle owners. How likely is your sample to contain 20% or more who own Harleys? So I've got two different proportions here, and what I want to pay attention to is this one where it says this word all. So that tells me that's like a claim that's supposed to be true for everybody. So that's my population proportion. I want to check, does P hat, is it going to be my sample going to be 20% or more? And then what's my sample size here? It's 500. Do we know our population size? Not exactly by number, and this happens quite a bit, but what we have to assume here is we can try and figure out, well, what should the population size be? Is it going to be big enough to satisfy that large counts condition, or I'm sorry, not the large counts condition, but the 10% condition? So we can safely assume this will be true, that capital N is going to be much, much greater than 5,000. I use these two greater than symbols next to each other to say much, much greater than. Now, why do I say 5,000? And how do I even know that this is an okay assumption? This is supposed to be all motorcycles registered in the United States. I think it's pretty safe to assume there are more than 5,000 motorcycles registered in the US. Okay. Now, why do I say 5,000? Well, in that case, then, our 10% condition, N, is it less than or equal to 10% of my total population? 500 is indeed less than or equal to 10% at a minimum of 5,000. So as long as our population is more than 5,000, which I'm going to assume it is, then my 10% condition is satisfied. And that's a reasonable assumption to make, and you guys need to get in the habit of doing that. Okay, that's a perfectly acceptable thing to do. The other condition we need to check before we go through anything is going through the LCC. Are we going to be able to say that the sampling distribution is going to be approximately normal? So we take a look. This one, our formula for this was N times P, is it greater than or equal to 10? And N times 1 minus P, was this greater than or equal to 10? Okay, so let's take a look. N is 500, and our probability of success in this case, remember this is P, not P hat. This is the supposed P, so that's 0.14, and that is indeed going to be greater than or equal to 10. And then so is 500 times 1 minus P, or 0.86. That is also going to be greater than or equal to 10. You notice that I'm not actually even writing out what the value is. I'm going through this in my head and I say, well, what's 10% of 500? That's 50. That's a reasonable thing to say. Yeah, that's going to be absolutely greater than 10. So our conditions are satisfied. We can now say that we have an approximately normal sampling distribution. Pretend that it looks normal and not like a weird wave in the ocean. But then we've got a mu sub P hat right in the middle of that approximately normal distribution. And that mu sub P hat is supposed to be equal to P, which is 0.14. Now I want to check to see 0.20. That's what I want to be looking at. This is the sample that I'm interested in. What's the probability that my sample is going to be 20% or more Harley owners in a sample of 500? So that means I can calculate a z-score that's going to correspond to my probability being greater than or equal to 20%, right? So the way that works is I take that same formula that I was working with, my observed sample, that's my p hat, divided by the average sample, that's sigma p hat, and we divide that by sigma p hat. So this is just the same thing as x minus mu divided by sigma. We just translated everything into p hats. So my p hat that I'm expecting to see is 20% Harley owners. The claim, or the average p hat, is supposed to be 14% Harley owners, and then I'm dividing by this standard deviation formula, which was p times 1 minus p divided by n. My p was the 0.14, not 0.20. This is p, not p hat, so be really careful about that. Times 1 minus p 1 minus 0.14 is 0.86, and then dividing this all by 500. Now, important to note, this 500 in the denominator, that is still in the square root, so everything, the entire fraction is inside the square root. And you can do this all in one fell swoop in the calculator if you want, but I'm going to do it in 2 steps. That's 0.06. When I punch this into my calculator, I end up with a 0.0155 value. And when I calculate all of that, or I do that division, I get a z-score of 3.87. Now, if you're looking for 3.87 on your z-table, you actually won't even find it, will you? Well, what that means is that z-table, that 0.3.87 is way far on the right of my z-curve, of my normal curve here. So effectively, the area for any z, or the probability that any z is more than 3.87, it's essentially non-existent. It's approximately 0. Okay, so the probability that if this claim is true, that 14% of all motorcycles registered in the US are Harley owners, are registered to Harley owners, and how likely am I to get a sample that's more than 20% Harley owners? Effectively 0. It's incredibly unlikely with that large of a sample size. Okay, so let's go ahead and take a look at the next example. Alright, so I'm going to try and go through this example quite a bit quicker. Notice that how I mark my text and all the things that I write down, try and work alongside of me rather than reading what I'm doing, because I am going to move fast. So an online retail company that rhymes with Amazon advertised that it ships 90% of its orders within 3 working days. I select an SRS of 100 of the 5,000 orders received in the past week for an audit. It reveals that 86 out of these orders were shipped on time. So I'm going to write down my givens here real quick, the things that I marked and I noticed that were going to be true for everything. Alright, so here we can see that 90% of all of its orders are supposed to ship within 3 days, so that's my population proportion, right? My sample was 86 out of 100 orders that were shipped on time, and my sample was only 100 out of a population of 5,000 for this past week. That's my population of interest, so that's my capital N. So from here, I can go and check my conditions for inference, which again are my 10% and my LCC, so let's go ahead and check those. Alright, so my LCC is satisfied, and so is my 10% condition. My sample 100 is less than 10% of 5,000, so I can go ahead and calculate probabilities of these sorts of things. I'm going to go ahead and jot down also my mean and standard deviation of the sampling distribution, because I know I'm probably going to be able to work with those. Alright, so now I'm ready to go ahead and actually read through this question and see what am I going to actually have to find. So if the company really ships 90% of its orders on time, what is the probability that the proportion in an SRS of 100 orders is 0.86 or less? So what is the probability that my sample proportion is less than 0.86? So drawing out that normal curve, the mean of that normal curve would be 0.9. And then 0.86 is going to be over here. So we know it's going to be less than 50% chance, but we want to know exactly how unlikely that's going to be. Okay, so I can put this into a z-score formula where I have my p hat 0.86 minus my p 0.90, divide that by my standard deviation of 0.03. And when I punch all that into my calculator, I'm going to get a z-score of negative 1.33. And I can go ahead and take a look and see what that is in my calculator, or on my z-table, or if I don't have a z-table handy, I can do the normal CDF calculations. Okay, so when you don't have a calculator handy, you can use websites. Like I said, I'm going to show you this one, and I will link it on Google Classroom for you to see. But here's a handy binomial CDF, not a binomial, excuse me, a normal CDF calculator that you can use. Alright, so here's this website that is a normal CDF calculator. It just asks me to enter in the mean of my distribution that happens to be normal, and in this case it was 0.90. My standard deviation was 0.03, and then I wanted to look at everything below 0.86. That was my observed value, right? So this may change, but it's like your lower bound and upper bound, right? So in this case, this one below, that would be considered my lower bound, okay? Or my upper bound, excuse me. And when I click OK, it gives me this value. It even shades it. So make sure you draw this picture. You don't have to put down all the standard deviations, but make sure you shade the area appropriately. And I get an area of 0.091. So with that area, I have to make sure that I do write in the normal calculations, just like I've done before, where I would consider how somebody else should write this into my calculator, with my lower bound being some number very, very low, close to negative infinity. So I'm just going to go negative 999. My upper bound was the observed value, or my p hat, 0.86. And then my mean was 0.90. That's my mu. And then my sigma was 0.03 that I punched in there. Okay, so there's a lot of different ways that you can go through this, but either way, we are going to end up with something very close to this 0.0912 or 9.12%. Okay, so let's go ahead and take a look at how we interpret this next part. So Critic says, aha, you claim 90%, but in your sample, the on-time percentage is less than that. So this 90% claim is wrong. Explain why your probability calculation in A shows that the result of the sample does not refute the 90% claim. So what this person is saying is they're calling BS on you, essentially, right? They're saying, hey, Cramazon, you're supposed to send 90% of your orders on time within 3 shipping days, but you had a sample of 100 where only 86% of those went out on time as you advertised. So that must be false advertisement. Well, here's what we can actually say. If we assume that claim is true, if we assume that 90% really are going out on time, how likely were we to get a sample of 86% go out on time? 9.12%. Now, is that 9.12% unlikely? Yeah, it is low. That is a very low probability. But is it so low that this couldn't have happened just by chance alone? That maybe the auditor just got unlucky in this case and saw a few more go out that were a little bit late? In that case, I'm not so sure. Right? Anything below 5% we would consider very unlikely, so unlikely that we would start to cast doubt on a claim. But this 9.12%, it is low, but not so low that it couldn't have happened just by chance alone. So I'm going to go ahead and type out what my response to this might look like. So if I assume that the 90% claim is true, then I have a 9.12% probability of having a sample selected where only 86% of my shipments leave on time. This is low, but not so low to make me doubt the claim. And that's this example. Let's go ahead and take a look into the next one. Alright, so for our last example, I want you guys to try this one on your own and then check your work against what mine looks like. Get to it! So there you have it. You see where we get our mean of p hat. We find our standard deviation by making sure we check our 10% condition. We know it's approximately normal by checking our LCC. Again, all things you need to do before performing any kind of inference. Then we went through and calculated our z-score and got a z-score of negative 2.08, which is going to be a pretty low value when I look at my table. Now, I didn't have a z-table handy, so I used my normal CDF calculator with a lower bound of negative 999 and an upper bound of 0.67, the observed value. My mean was 0.70, sigma was 0.0144, and I got 0.0186. that was 0.0186. It's a 1.86% chance. So if I assume that the claim is true, there's only a 1.86% chance of getting a sample like this by chance alone. That's very unlikely. So what that tells me is that, hey, you know what, maybe this claim, 70%, maybe it's not really true. Maybe that value is actually closer to 67%. All right, that's it for section 7.2 and sampling distributions of sample proportions. Have a wonderful day and get started on your homework.